And I'd also like to extend my thanks to DataWorks as well as also Sarah, because she's the one who extended the invitation to me to give a talk on my tolerance package for R. And so this was a joint, well, recently the updates that I'm doing is a joint work with my former student, Kadai Chang, who is an assistant professor down at UNC Asheville. Brief acknowledgement for my funding through the Chan Zuckerberg Initiative for these updates. And an overview, just preliminaries regarding tolerance regions, if you're not familiar with those, followed by the package, as well as just some of the functionalities that are available in my package. And I'm going to briefly show just some screenshots for the Shiny app. So I wasn't sure exactly if I was going to have access to be able to go through and do it. So sorry, that part will be static, as well as some of the other visualizations that I have in here. And then just ending with a few resources. And then down below, I have the materials, including the presentation slides, which also you're obviously able to get from DataWorks, but also the R code for this is available up on my GitHub page. And this is actually just a subset of a much longer presentation that I'm going to be doing a recording for and putting up on my website. So tolerance regions. So you're all surely familiar with confidence and prediction regions. So based on a random sample, you know that with a confidence region, you can provide regions for an unknown population parameter, like a mean or a variance matrix, for example. Prediction regions, you would be able to provide regions for one or more future observations from that sample population. Now, statistical tolerance regions, which actually have quite a lengthy history back to the 40s with Wilkes and Wald, that provides regions that are expected to contain at least a specified proportion of the sample population. So there's many applications that are out there. So tolerance intervals, I'm saying, for the univariate setting, which I'll be highlighting a lot of those, include clinical and industrial studies, statistical quality control, environmental monitoring, and then setting statistically based engineering design limits, which was really my first exposure when I worked for the Naval Nuclear Propulsion Program. And then just to tie this back actually to what Sarah was talking about, this is used quite extensively with bioequivalence testing. So like the FDA has these curves, I think they're called F1 dissolution similarity profiles. And my colleague Thomas Matthew has actually developed tolerance regions to use that as a means for doing bioequivalence testing for those profiles. And it does show up in quite a few regulatory documents, such as from the EPA, IAEA, and the NRC. And regarding my colleague Thomas Matthew, as well as my colleague Kelly Muthu Krishnamurthy, they have a very good reference on the topic, and it's now a little bit outdated, but still, I would say comprehensive up until that time point. So this is the most mathematical portion that I have for this talk, and this is just giving the definition. If you have a random sample of size n, of continuous random variables, and they have cumulative distribution function fx, parameterized according to that theta parameter, we can then say we also have another random variable x, draw from that same distribution, but independent of the random sample. We then can define our one-sided upper and one-sided lower tolerance limits based on the criteria in 1 and 2. And so what those definitions are, if you're familiar with confidence intervals on quantiles, that's all that those definitions are. And then we can also do a two-sided tolerance interval, which is given by the criterion in 3. And so that probability statement is actually on a central proportion of the sample population. But then we can also do an equal-tailed tolerance interval, which is given by the criterion in 4, which is a little bit more restrictive because you're saying that no more than 1 minus p halves of that sample population is out in the tails. So I'll now move into talking about my tolerance package. And this is, I always say, my shameless self-promotion slide on the package. So I first released this in 2009. It includes tolerance intervals, many of them that I'm going to briefly highlight here for numerous parametric distributions, especially the univariate settings and non-parametric setting based on order statistics. Got various regression models as well as the multivariate settings, and also there's visualizations, which have recently been updated based on the grant that I have. And it's been used by NASA, 3M, Ecolab, many other institutions. This is just from me knowing based on them contacting me and asking questions about what's doing in the package. And then I'm just also showing just like the number of monthly downloads for this from 2017 to 2021, respectively. So it is highly used out there, and I'm proud of it, and I enjoy taking questions about it whenever they come up. So this is just a subset of some of the functionality in tolerance. So first of all, for the continuous distributions, we do tolerance intervals, normal, log, normal distribution, gamma, log, gamma, and also Laplace distribution. Discrete distributions, which these show up a lot for acceptance sampling plans, would be, for example, binomial, hypergeometric, and negative hypergeometric, as well as the Poisson. And for the non-parametric procedures, in particular for the univariate ones, which are based on order statistics, I'm going to be highlighting that first one there, but also we can do beta expectation non-parametric tolerance intervals. That's just equivalent to a prediction interval, but again, based on order statistics. as well as the necessary sample size determination calculation for non-parametric tolerance intervals. For the regression setting, linear, nonlinear, non-parametric regression. I also have ones for autoregressive settings, as well as I'm working on one with a spatial setting with one of my advisees. Multivariate tolerance regions, we could do multivariate normal in here, multivariate regression, as well as the one I'm going to highlight here, which is a non-parametric multivariate tolerance region, which is going to be construction of hyperrectangular regions. The visualizations that we have in here are plotting a control charts, histograms, and scatter plots, as well as an OC curve for K factors. And again, back when I first did this, everything was really done in base R graphics. And part of this grant was to update something where we already had the infrastructure in place. And so all of this has been updated using Plotly. Then just a basic format for a tolerance function I have here is dist.tal.int I've written up there. So basically the DIST gets replaced with some shorthand for whatever distribution of interest. For example, normal tolerance intervals, NORM tal.int. And these are the basic types of arguments that you would see in most of these functions. Obviously, there's a data argument for you to input your data. Alpha is going to correspond to the significance level, which means 1 minus alpha gives you that gamma that I've been using for my confidence level. P is the content level. Psi, if you're going to do one or two-sided setting, if you're doing a univariate tolerance interval. And then method, almost all of the methods that are out there are approximations. And so there's various approximations that have been developed over the years for a lot of these settings. And so I have various ones that are coded up for a given distribution. And then the function outputs basically will usually be parameter estimates, typically MLEs, for the parametric tolerance intervals, and then of course the requested tolerance intervals or regions. So for normal tolerance intervals, we just assume that we have an IID sample of size n from a normal distribution, mean mu, variance sigma squared, x bar and s squared, the corresponding sample mean and variance. And then the lower and upper tolerance limits would then be given by the equations in 5, which would also be followed directly from the slide I had earlier with the general definition. And it's the sample mean plus or minus this K factor times the standard deviation. And that K factor I have right here is just indexed by H, where that index set is 1, 2, or E not the natural number, but rather E just denoting an equal-tailed tolerance interval. And so these K factors are derived in a way that we capture at least a proportion P of that sample population with the given confidence level gamma. So I have 4 functions for doing K factor calculations and tolerance. The first one is K factor, and they do begin with a capital K. That one is just going to do the calculation of those 3 K factors under the normal setting, for one-sided, two-sided, as well as equal-tailed setting. I also have this function there that tabulates them under numerous user-provided conditions. I also have one that estimates K factors for simultaneous tolerance intervals based on normality. And then I also have, I had already alluded to like a normal or an operating characteristic curve regarding K factors, and that can be done through the norm.oc function. So the first example I'll give here regards the thickness of silicon wafers. There's 100 silicon wafers, and the thickness on those were collected resulting from a chemical vapor deposition process in a semiconductor plant. Thickness is measured in angstroms, and the data appear approximately normal. And I'm going to construct a 95-95 two-sided normal tolerance interval to quantify where we would expect at least 95% of those thickness measurements to fall with 95% confidence. So the function, as I had just said earlier, normtal.int is what I would implement, and then x equals wafer. That's the name of the data set that I have in here is wafer. And then alpha p correspond again to the significance level and the content level. Side, I'm doing a two-sided, and I want to use the exact method. Now, if you look at the help file that I have, there's many methods I have in there, and I mainly have those in there for historical reasons, because in the past, you had to do a lot of approximations for the calculations of these K factors. And they still show up actually in some of the regulatory documents that are out there. But the exact method is actually solving the integral equation for the K factor. So it is the one that you should implement, in other words. And so the output, very simple here for this setting, just gives you, like I said, the X bar would be the sample mean, and then the two-sided lower and two-sided upper tolerance limits, we would be saying with 95% confidence, we would expect at least 95% of the thickness measurements to be between roughly 420 and 480 angstroms. And then down below are a couple of the visualizations you can do, just the histogram as well as the control chart for these if this was actually processed data. And then overlaying on there are the tolerance intervals that I just calculated right up there of 420 and 480. So of course, you're not always going to be in a normal setting, and I have a number of functions in there for other parametric distributions, and that goes for discrete as well as continuous non-normal distributions. The tolerance intervals for the discrete distributions mostly use the method due to Hahn and Chandra, which requires that the discrete distribution be stochastically increasing in the main parameter, such as like the mean or the location parameter. And then we use the confidence intervals on that parameter to then construct the corresponding tolerance intervals. For the continuous univariate populations, but where a distribution assumption isn't made, we can then turn to doing the non-parametric tolerance intervals, which these are based on order statistics. And so I'm going to briefly illustrate the binomial, Weibull, and non-parametric tolerance intervals procedures. So the first one I have here is defective chips for quality control purposes. The location of chips on a wafer is measured on 30 wafers, and there were 50 chips measured on each wafer. Chip is recorded as defective whenever there's a misregistration in terms of horizontal and or vertical distances from the center that occurs. And so we have a total of 50 times 30 or 1,500 samples of chips for which we can calculate the proportion of defects. Going to construct a 99-95 two-sided binomial tolerance interval for a future sample of size m equals 50. So using this function now, bin tau.in for binomial tolerance intervals, input the data as usual. N is going to refer to the sample size. In this case, so I just put 50 times 30 to be explicit with respect to what I said on the previous slide. And then M is going to be the future sample I'm looking at of 50. And again, setting everything else similar to what I have. The method there in this case refers to CP, which is the Copper-Pearson method for the construction of the confidence interval on the binomial proportion. Because there's, you can look in the literature, there's a whole host of ways of being able to construct confidence intervals for proportions, each with their own performance properties in terms of coverage and expected length. And I have a lot of those coded up in here as well as possible ways for doing the confidence interval calculation that underlies the tolerance interval calculation. And so in this case, the two-sided interval would then be given by 4 and 21. And down below is again the control chart. If you were to look at the data that was that I referred to as defects as a set of process. Now, serum creatinine for the next example, blood test to measure the creatinine levels in the blood. Reference ranges for creatinine levels are typically between 0.7 and 1.3 for males and 0.6 and 1.1 for females. And I'm going to construct a 95-95 two-sided Weibull tolerance interval for serum creatinine, and this is from a sample of 596 healthy individuals. And I did not I did not distinguish between the sexes. So this is just for the entire sample that I have here. So then in this case, my function is ext-tau.in for extreme value distribution. And the two distributions that I have in here are the Weibull and the Gumbel. So the argument that you see there is dist equals Weibull, obviously doing the Weibull distribution. And then so the output in this case, the MLEs for the shape parameters are given there, as well as the two-sided tolerance interval, the 95-95 tolerance interval for a Weibull distribution. And the next one I have is a subset of data from a larger study on survival times in months for 121 breast cancer patients. I'm going to construct a non-parametric 90-90 two-sided tolerance interval. Again, this is based on order statistics for the remission times. And such a tolerance interval could provide reasonable expectations for the duration of long-term care of individuals. So in this case, my function is np tau.in for non-parametric tolerance intervals. Again, just input basically everything that we have there. I'm not going to say too much about the method there, but that's corresponding to Wilks. That's who originally worked on the non-parametric tolerance intervals back in the 40s. But this is just a different way of basically being able to summarize the order statistics, which I'm not going to go too much into. But the output in this case, again, this would be based on the corresponding order statistics based on those confidence and content levels. And so we would have 5 and 129 in this case. So, of course, this is all univariate settings, and you're going to be wanting to do more complicated modeling. So we can, of course, incorporate covariates in here as well. And so I already mentioned that the regression settings I have available in the tolerance package includes linear, nonlinear, non-parametric regression, as well as multivariate linear regression. And while this was, I believe, the first paper that developed pointwise tolerance intervals for linear regression models, in my 2013 paper, I revisited that, but then also proposed procedures for doing pointwise nonlinear regression tolerance intervals as well as non-parametric regression tolerance intervals. And there's also various approaches that are out there for simultaneous tolerance intervals, but I currently don't have those implemented in the tolerance package. So the data I'm going to look at is from what's called the Scenic project, and the study's primary aim was to determine whether infection surveillance and control programs help to reduce the rates of hospital-acquired infections in US hospitals. And this was a random sample of 113 hospitals from original 338 hospitals that were surveyed. And there's a number of variables that are in this data set, but I'm just going to be looking at two of them as predictors of infection risk. The two predictors were the length of stay of all hospital patients, and then the ratio of number of chest x-rays that were performed to number of patients without signs or symptoms of pneumonia multiplied by 100. I'm going to construct pointwise 90-90 two-sided linear regression tolerance intervals, including for a new observation that has an average length of stay of 12 days and a chest x-ray ratio times 100 of 50. So the first thing that you need to do is, instead of just inputting directly the data, you're going to be inputting the linear models fit for it. So my first line right there is just the linear models fit where I'm regressing the infection risk on x-ray as well as the length of stay. So I input that in there, and the function is actually regtal.int. This is just the development name that I gave to the function that I currently have on GitHub because we organized the output a little bit differently. So it'll eventually replace what I have in my package, which is the regtal.int function. Anyhow, you input the linear models output right there. And then if you have new data for which you want to construct these tolerance intervals, that's where you would use the new.x argument. And this closely mirrors like if you're using the predict function in R on linear model output. And so your input there is going to be a data frame, and then the variable names need to match the names of your predictors that are in the original linear model fit. So in that case, I'm doing 50 and 12 for those two variables, and the rest of the arguments are similar to what we've already shown before. And so right here, this is just a little bit of the output. I'm just showing the last four observations, 110 to 113 in the data set. And then if you have any new observations, those get appended to that data frame output. So in this case, that last observation where it has an NA for a value of Y, that corresponds to the new X values of X-ray 50 and length of stay of 12. So then if we're doing either a single predictor or two predictors, then we can get the corresponding figures available in my package. And again, this is of course what you can interact with. So I just have a static presentation here, but that's the blue points are obviously the data, and then the least squares plane given right there, as well as the corresponding two-sided 90-90 tolerance planes are given there in red. So now, of course, if you don't want to go in a regression setting, you just want to treat the data as strictly multivariate, then we can also do tolerance regions for those settings as well. So just as in the previous settings, multivariate tolerance regions serve the same purpose and have the same interpretation, but just granted in a multivariate context. And so there's far fewer procedures out there for multivariate tolerance regions. But as I already highlighted, I have capabilities for multivariate normal, as well as multivariate linear regression. And then also the one I'll highlight here, which is non-parametric hyperrectangular tolerance regions. And this is something I worked on with my colleague, Thomas Matthew, where we developed these regions for constructing hyperrectangular reference regions. And we use data depth to be able to provide a center outward ranking of the data, followed by bounding the region of a depth trimmed version of the data. So even though this is in the context of a hyperrectangular geometry, we could actually go back to something Tom was talking about with the convex holes. We can use this depth-based trimming to do convex hole peeling and get tolerance regions for that setting as well. But ascertaining the coverage properties of those is a bigger, more daunting task to try to see if it's actually doing a good job. The example I have here regards adolescent kidney function reference regions. And the kidney function laboratory tests include a urinalysis to screen for the presence of protein and blood in the urine. There's a Bun test to check for waste product in the urine, as well as tests to obtain the estimated glomerular filtration rate, the EGFR, and that's used to detect the presence and cause of kidney disease. And there's actually not as much information out there regarding normal reference values for kidney function in adolescents, and that of course can impact how physicians would diagnose and manage diabetes in that population. So I'm going to construct here non-parametric 95-95 semi-space rectangular tolerance regions. And the semi-space terminology that we use is just because for the dimensions that you have for your multivariate data, you may not want to have a two-sided interval. You may only need a one-sided interval because, for example, the lowest limit is going to be 0. So that's what I'm just using that terminology of semi-space for. And that's going to be used to represent the reference regions of normal adolescent kidney function. And we're going to look at the males of this sample. This is based on 2,529 subjects in the reference sample. This comes from the N. Haynes data. So the function that we have in here is npmv-tol.region. So you would input the data yet again, alpha and p, and then the depth function for doing the trimming in this case is the elliptical depth function. And in our paper, I explained a lot more of these different depth functions that can be implemented in here. Then I specify semi-space. If I wanted to just have two-sided intervals for each of the dimensions of my multivariate data, I would specify central there. Adjustment is a little bit of an adjustment factor. I won't explain too much right here. But semi.order, that's an argument that would say, or you would enter in as a list, which variables have either the two-sided or one-sided limits that are required. So in this case, when I say lower equals null, that means that there is none of them I'm constructing just a lower limit for. Center, I have 2 to 3. So that says that the index for my variables or my multivariate data set, the second and third variables, those are going to be requiring two-sided intervals. And then the upper is the index for the other, for any of the variables that I want just a one-sided upper limit for. And so in this case, it's going to be the first dimension of my multivariate data set. So that translates to what you see down below for the output. So these are the 3 variables that we looked at: UACR, uric acid, and serum creatinine. And then UACR, that's the first variable in here, and that's the one that's requiring just a one-sided upper limit. The other 2 are requiring the two-sided limits. And then so this is one of the figures that we construct for that. So you would then be able to look at the pairwise scatter plots for each of these variables in here. And the reference range, or the tolerance region that we constructed, is what's shaded in there, obviously, and it's between the limits that were just reported on the previous slide. And then the points are color-coded according to whether or not they fall inside or outside that region. So that's why sometimes, like if you look at the figure over to the right, you see some of those red points that are within that appear to be within the reference region, but that's just because it is actually an extreme value relative to what would be the UACR variable. Sorry, the labels are a little bit small in that setting, but that would mean that that was actually extreme with respect to that other dimension. So as I said, also, there is a Shiny app that's available, and it basically does everything that we currently have in the package, but it's just done in a Shiny app framework. So then over on the left-hand side of the menu right there, you just go down and you can do either data generation or upload your data for which you'd like to do the tolerance interval calculations. And then you would select what distributional assumption you're planning on making, or if you just want to do it based on order statistics for a non-parametric setting. So down below, that's just showing the random generation of the data for this setting, which is a normal setting. And then down below, you would then get a summary on the tolerance intervals, namely just like the two-sided tolerance interval in this case, which is being requested. And then any of the visualizations that you want, in particular, like the histogram with the tolerance limits overlaid on there. So then just some of the resources, my original paper on the package, as well as my GitHub repo, as I already mentioned, as well as the link for the Shiny app, which was actually at the bottom of the previous slide, or a few slides ago. So those are some additional resources for it. And then also, I'm happy to take any questions, or you can feel free to reach out to me at any of these meetings.
All right, well, he's done 2 minutes early, and so we've got time for some questions.
We use your tolerance.
Oh, good. Okay, I'll add that in there. Okay, that sounds good.
No.
No, not even in the generic detail.
Okay. Yeah. I can't.
Okay, fair enough.
So are there any questions for Derek?
I would like to ask a question, just kind of generally, as far as the benefits of using a tolerance interval or tolerance region versus using a traditional confidence interval.
Yep.
Kind of what you're asking, what are some practical applications for that?
Well, going back to what I was saying with the regulatory documents, like for example, if you're talking about the FDA, they're going to have, for example, some sort of specification limits, or even NRC applications as well. There's going to be some sort of specification limits that whenever you have some sort of test data, you need to be able to show that with a certain degree of confidence that you're going to have at least a certain proportion of those that are able to meet that specification limit. So that's moving beyond just simply doing an uncertainty band, if you want to say, around a parameter. You're actually trying to quantify a certain amount of the population. So then if you're showing that that's actually able to do it based on, whatever your test data is, and it falls within their specification limits, then you'll get approval.
And just in a generic sense, to Dr. J's comment, we use it to trap percentiles.
Okay,
Right. And it's really, really effective. We really use it a lot.
great. Oh, that's good to hear.
And you have, you showed that three-dimensional plot where you tracked a linear regression setting. And that's in the package itself.
Yeah, that stuff's on my GitHub page right now because that's stuff that we just worked on this past year. I'm planning on pushing all of that together for one big update to the package. So I didn't want to kind of do it piecewise. So there's a lot of new, basically all of the current visualizations which are in there, which are all just based on base R, those are being replaced now with stuff that's done in Plotly so that it's more interactive. Because back in the day, even with my other big R package that I had, everything was done base R because you really didn't have like the ggplot infrastructure back then or anything. So obviously the graphics has come a long way over the past 10, 15 years. And I just haven't had the time to be able to do that. And now that's exactly what this grant was for, is that it was for able to improve something that you had the existing infrastructure for. So I was able to finally have the time for that over the past 2 years because of that. But yeah, that's my plan is the beginning of the summer, actually. So another month or two, we should be ready because we have all the documentation ready to go for it.
Any other questions?
I'll get one. Jeremy Werner, DOT and EEG Science Advisor. It's not always the case that you know ahead of time whether you want a one-sided tolerance interval or a two-sided tolerance interval.
Mm-hmm.
Is there any consideration for that or no?
Well, I guess the applications that I've always seen is that it would kind of make sense that you would want, for example, like I'm talking about from the engineering standpoint, that you might have some sort of upper limit or some sort of upper spec limit. Like, for example, I remember an application worked on with libel regression models. Yeah. And, it doesn't matter quite really how low it gets on there. It's just you don't want it exceeding that threshold up there. And so that's like a case where you would have just a one-sided limit because you're just wanting to show that that upper is not going to actually hit that upper spec limit.
Yeah, I don't have an exact application for a tolerance interval, but for instance, for like a confidence interval, if you're trying to detect a signal, right, then you want to make that choice before you detect it or not.
Yeah. Yeah. And I think that would start to, I guess, harken back to when you're doing just like basic control charts, and even going back to like what Tom was showing, and they were doing the sample mean plus or minus 3 times standard deviation. And instead, if you know what setting you're kind of in regarding the control, doing the calculation for the control limits, then basically you can apply that same logic for when you're doing the calculation of the tolerance limits.
Thank you.
All right, well, let's thank Derek again.